In the world we live in today, fossil fuels are our main source of energy. However, these non-renewable fossil fuels contribute to a global climate change. For example, to create plastics, ethylene oxide is produced to then form ethylene glycol. The ethylene glycol then becomes polymer polyethylene terephthalate, which can be used to make soda bottles, polyester yarn, and clamshell packaging.
This synthesis of ethylene oxide, however, relies on energy from fossil fuels and releases 1.9 tons of CO2 per 1 ton of ethylene oxide, harming the environment. To date, ethylene oxide has been produced from ethanol to ethylene and finally to ethylene oxide, relying heavily on energy from fossil fuels to kickstart the reaction. However, here at UW-Madison, the Schreier lab looks to increase sustainability during the synthesis of ethylene oxide.
Instead of this aforementioned wasteful process, the Schreier lab uses the chlorination of ethanol into chlorohydrin, or 2-chloroethanol, to eliminate the great need for fossil fuels, as explained by Lucky, Wang, and Schreier in electrochemical ethylene oxide synthesis from ethanol. The chlorination of ethanol uses the chlorine atom as a catalyst, which is a species which provides an alternate pathway for reaction. A catalyst is consumed and then regenerated in different reaction steps. Since this catalyst is present in the same phase as the reactants, it is considered to be a homogeneous catalyst. The chlorine does its job as a catalyst and increases the rate of the reaction by lowering the activation energy, therefore requiring less heat from burning fossil fuels. With a lower activation energy, this creates a lower energy barrier, allowing a larger fraction of molecules to proceed in the reaction.
The original reaction is non-spontaneous due to being thermodynamically unfavorable with a high delta G. However, by electrolysis, it becomes a spontaneous redox reaction. In order to set up the reaction and aid in electrolysis, it is necessary to set up an electrolytic cell with 2 chambers separated by an alkaline-anion electron exchange membrane, a porous strip that allows for movement of ions but restricts the mixing of the products. Then, an anode and a cathode are placed into a solution of 0.5 molar NaCl and 0.6 molar NaClO4 so that we may produce chloride ions as NaCl and NaClO4 dissociate in water. In the electrolytic cell, oxidation happens at the anode end and reduction happens at the cathode end. In order to understand this reaction, it's important to understand the purpose of this and how electrical current allows this reaction to occur. As Bogokich explains in Fundamentals of Electrochemistry, at the surface of the electrode at the anode end, there is an oxidation reaction with the solution which produces electrons. These electrons then flow to the cathode, which generates an electrical current and lets a reduction reaction take place on the cathode end. In this way, a redox reaction can occur. The chlorine is first oxidized at the anode end to create a free radical, which then combines with the ethanol to form 2-chloroethanol. The electron from the chlorine ion is then transferred to the cathode, which then reduces a water molecule, forming hydrogen gas and hydroxide ions. The 2-chloroethanol and the hydroxide ions then react with each other to form ethylene oxide while recovering the chloride ion.
A reminder for this reaction, the anode and the cathode do not need to be separated into different solutions. This is because there exists an anion exchange membrane which allows the chloride anions to pass through but otherwise keeps the reaction separate. This is important because we do not want the 2-chloroethanol to become ethylene oxide while in the analyte because it is likely that it will be further oxidized. Instead, the reaction is carried out by siphoning analyte and catholyte into a separate container, where the strongly basic catholyte solution provides a suitable environment for the cyclization of the 2-chloroethanol.
However, when chlorinating the ethanol, there is the possibility of the chlorine bonding to the alpha carbon, which would be an intermediate form for acetic acid, not ethylene oxide. This occurs because less energy is required to replace a hydrogen on the alpha carbon than the beta carbon. This occurs because free radicals are more stable when the number of electronegative substituents connected increases. As the website Master Organic Chemistry, Selectivity on Free Radical Reactions explains. In this case, the alpha carbon has both the carbon and oxygen atom bonded to it, while the beta carbon has only one other carbon and a hydrogen atom attached. Because hydrogen is less electronegative than oxygen, the molecule is more stable when the free radical is bonded to the alpha carbon. This difference in structure helps to demonstrate the CHEM 109 idea that structure governs function, showing that a structural isomer with the same formula but different connectivity can create a different product with a different function.
In order to create more of the desired 2-chloroethanol, the Schreier lab uses boron-doped diamond anodes and cathodes to more easily oxidize chloride into chlorine-free radicals and lower the overall energy of the product, 2-chloroethanol. It is important to use a boron-doped diamond because this is a material which oxidizes chloride at lower potential than water, meaning the desired oxidation of the chloride atoms will occur rather than creating hydronium ions through oxidation of water, as explained by McPherson in a practical guide to using boron-doped diamond in electrochemical research.
The boron-doped diamond also affects the energy required to produce products in this reaction. If we look at the activation energy graphs for 1-chloroethanol and 2-chloroethanol, we see that making 1-chloroethanol requires less energy than 2-chloroethanol, as 1-chloroethanol has a smaller change in Gibbs free energy than 2-chloroethanol. However, when we introduce the boron-doped diamond anodes and cathodes, the change in Gibbs free energy is now lower for 2-chloroethanol, thus making 2-chloroethanol more favorable and allowing the entire reaction to be more efficient. Because the change in Gibbs free energy is lower, that means less heat is required to make the product of 2-chloroethanol. Therefore, with less heat required, fossil fuels are burned less, thus increasing sustainability. This demonstrates the CHEM 109 idea that energy governs change by showing that changing the energy pathway allows for more reactants to change into the desired product.
Overall, this changing of energy pathways opens up a realm of possibilities as we create materials, allowing us to find less energy-intensive pathways, increasing sustainability, and helping the environment.